Further ado, tonight's speaker is Dr. Jeff Andrews-Hanna. Jeff got his bachelor's at Cornell University in Ithaca, New York, and his PhD at one of my favorite universities, since it's my PhD alma mater as well, Washington University in St. Louis. And tonight, Jeff is going to be talking about the dark side of the moon, or do you believe in gravity, right?
Sure. All right. Thanks, Tim, for the introduction. Thank you. So I framed my talk around this idea of the dark side of the moon, which is something that comes up a lot in pop culture. We see this quite a bit, beginning with, of course, Pink Floyd's famous album, The Dark Side of the Moon, in which I'm told that they were referring to lunacy rather than lunar science. It's a little bit of a subtle distinction, if you ask me. But since then, the dark side of the moon comes up a lot in popular culture, oftentimes symbolizing the mysterious and the unknown. Recently, we saw this in the latest Transformers movie, Dark of the Moon, where the dark side of the moon, this unknown, unexplored place where the Transformers had a secret military base and they're waiting to take over the Earth. Because anything could be there on the dark side of the moon. I mean, really, who knows? People love conspiracies, especially conspiracies involving NASA. So I'm going to show you this secret image I'm not supposed to show you, revealing the dark side of the moon. This is a very grainy image. And the reason why it's grainy is because all conspiracy theories have to revolve around a grainy image. And also because this image of the moon was taken from Mars. And this is an actual image of the moon and the Earth. And in this image that NASA doesn't want you to see, because they've been hiding the fact for decades, that not only does the moon have a dark side, but the Earth has a dark side too. That's right, and I don't want anyone to panic, but as I speak and as you sit here and listen, we in Tucson are hurtling towards the dark side of the Earth at a speed of about 1,000 miles per hour. And literally, if you could look out the window, you would see the landscape being plunged into darkness. And it would stay that way until about 6 a.m. tomorrow morning when your alarm goes off. You get up, you walk the dog, you make breakfast, you go to work or school or whatever, and you repeat every 24 hours. Because, well, of course the moon has a dark side, and of course the Earth has a dark side, but really it's the night side, not the dark side. We've got a night side and a day side, and they change on a daily cycle as the sun rises and the sun sets. There's nothing mysterious about it. Pink Floyd doesn't write songs about the dark side of the Earth. There's not a secret Transformers base on the dark side of the Earth. It's just nighttime there, and we'll be there shortly. And the same is true of the moon. So the moon has a far side that's always facing away and a near side that's always facing the Earth. And I think in popular culture, people confuse the idea of the far side of the moon with the dark side. But in reality, because the moon always faces the same side at the Earth, an observer on the moon would always see the Earth staying in the same place in the sky, but they'd see the sun rising and setting as the moon orbits the Earth. And it would rise and set on about a 28-day cycle instead of our 24-hour cycle on the Earth. So if this is a little disappointing that the moon doesn't have a permanently dark side that's vast and mysterious, to make it even worse, the night side of the moon isn't really all that dark. This is a picture from the most recent solar eclipse that a friend of mine took. He went up to where it was a total eclipse. And if you could take your eyes away from the beautiful solar corona to the dark hole in the middle, that's the moon covering up the sun, and specifically, that's the night side of the moon covering up the sun. And if you look closely, even in the lighting in this room, you can actually see details on the night side of the moon. If I stretch the contrast more, that looks just like a full moon, because it's the same face of the moon that we see normally. But what's lighting it up if the sun is behind the moon? This is the moon illuminated in Earthshine. Because just like a full moon really lights up the Earth, a full Earth really lights up the moon. And in fact, you don't have to wait for a solar eclipse to see this. If you go out in a week or so and look at a crescent moon, if you look carefully, you'll notice you can actually see the unilluminated hemisphere of the moon, the night side of the moon. You can see that lit up in Earthshine. So I would argue there really isn't a dark side of the moon, at least not in the sense of a permanently dark, unknown side of the moon. Unless, of course, you think about it this way. Light that we see, visible light, only penetrates about 1/1000th of a millimeter into the lunar surface, about a micrometer. What that means is that all of our cameras and our eyes from Earth are only seeing the very, very, very topmost surface of the moon. That leaves the entire vast interior of the moon unseen, at least unseen in the traditional sense. So pictures are only skin deep. If there's a dark side of the moon, it's the inside of the moon. But unlike the sort of metaphorical dark side of the moon, the inside of the moon is not a complete unknown. We can say things about it. So we have a few different ways that we can probe the inside of the moon. One approach is using radar. So radio waves can propagate through rock to distances of 1 kilometer or so. And we've sent a few different radar instruments to the moon, both on the Apollo missions as well as more recently the Japanese Kaguya mission. And those radar sounders could probe to depths of about 1 kilometer. They saw things like layering in basaltic lava flows on the moon. So this is one way to reveal the lunar interior. But again, we're only getting the top kilometer, so there's a lot more down there to see. Seismic waves are another way to study the moon's interior. Seismic waves on the moon can propagate throughout the moon just like they propagate throughout the Earth. And we can measure those seismic waves and use their properties to try to understand the structure of the moon. Where do these seismic waves come from? Well, the moon has moonquakes, similar to the way the Earth has earthquakes. And there are also impacts on the moon, where either meteorites or man-made spacecraft have impacted into the moon and created seismic waves. This is another approach. We can image, or at least examine the interior structure of the moon. Seismic data is a little difficult, though, because there are only a few seismometers put on the moon back in the Apollo days. They're not functional anymore. We've got limited coverage. So my own personal favorite way to study the interior of the moon is with gravity data. So gravity, in some senses, is kind of an obscure field that's difficult for people to wrap their mind around, but really gravity is one of the simplest things out there. We all understand the basic idea of gravity. Gravity is what holds us down to the Earth, despite some people who claim it doesn't exist. Without gravity, we'd all go flinging off into space. So we're very happy that we have gravity on the Earth. Gravitational acceleration on the Earth's surface is about 9.8 meters per second squared, about 30 feet per second squared. The moon also has gravity, not surprisingly. Gravity on the surface of the moon is about 1/5 of gravity on the surface of the Earth. Now we know this in part because we sent astronauts there and they walked around, they didn't fly off. That 1/5 gravity means they did kind of a funny little, galloping bunny hop across the surface of the moon, but it was enough to let them walk. But we don't have to send people to the moon to know it's got a gravity field because we can feel it here on the Earth. People have been observing the lunar gravity field for millennia. All you have to do is go to the beach. The tide comes in, the tide comes out. You're seeing the effects of the moon's gravity field on the Earth. So that's another way we can measure it. But the Earth and the moon aren't the only objects out there with gravity. In fact, anything that has mass has gravity. Now, we all know people who think they're the center of the universe. I know that I'm not the center of the universe, but I am so important. I have my own personal gravity field. So I exert a pull on everything around me. It's a teeny tiny pull, but it's a pull. I have a gravity field that, in theory, could be measurable. This is what allows us to study the interior of planets. I've got a gravity field. You've got a gravity field. This table has a gravity field. Everything with mass has a gravity field and exerts a pull. And so we can measure gravity very precisely and use that to examine the distribution of mass. Now, gravity as a field is incredibly old. The earliest gravity studies I'm completely in awe of, because how do they measure variations in the Earth's gravity field? They use something called a plumb bob. This is a weight on a string. Basic idea is if you go up next to a very large, massive object, like a big mountain range, well, that plumb bob, that weight on the string, will be deflected a little bit towards that massive object. This took incredibly precise measurements, but people were doing this in the 1850s. One of the very first gravity studies of the Earth, using a weight on a string, revealed something just completely fundamentally new and important about the structure of the Earth. And that was looking at the Himalaya Mountains. So this was Sir George Everest and Archbishop Pratt of Calcutta decided to do a gravity survey of the Himalaya. So their idea was, well, we can see this mountain range, we can measure the height of the mountain range, we can guess at how much mass of rock is in that mountain range, and we can calculate what the gravitational pull of the Himalaya should be. Then they went out with their plumb bob and measured the gravitational field of the Himalaya, and it was not what they expected. In fact, it was only a small fraction of what they expected to see. And that's not because they did their calculations wrong. It's not because it was a windy day and the plumb bob was blowing all over the place, although I really don't know how they do this. It was because there was something fundamental about the structure of the Earth's crust below the Himalaya that people did not know at that time. Because if you have a mountain range like this, it's got a lot of mass within it, and that will deflect the plumb bob towards it. Yes, that's true. And if that's the end of the story, then Everest and Pratt would have observed the deflection they expected. In actuality, though, what we have, if this is the crust of the Earth and this is the Himalaya, below the Himalaya is a thick, thick crustal root extending down into the mantle. So we now know that the Earth has a low-density crust and a higher-density mantle, and that this is the arrangement in the Himalaya and in many other mountain ranges as well. It's similar to what you have with an iceberg. So yes, with an iceberg, you've got this mass of ice that's jutting up into the air. This would give you a positive gravity anomaly. But as we all know, 90% of the iceberg is hidden below the surface of the water. This ice has a lower density than the water that surrounds it. Because of that, this would give you a negative gravity anomaly, and in fact, the two happen to cancel out. And so if you were to try to measure the gravity anomaly from an iceberg, you'd detect a very, very small anomaly, a lot smaller than you'd expect from the 10% that you see. The same is true of the Himalaya on the Earth and of a lot of other mountain belts. This is just an amazing discovery made 150 years ago with weight on a string. This is the kind of thing we want to be able to do on the moon. But you can imagine if you could go to smaller scales with better data, you could detect more subtle things. So what if within the crust of the Earth, what if there was a dense object? Something like, say, solidified magma that forms a dense igneous rock. If this has a higher density than the rock around it, it should give you a positive gravity anomaly that with a sensitive enough instrument, something better than a plumb bob on a string, you could actually measure. All right, let's turn to lunar science now. So the first gravity observations of the moon actually occurred more than 50 years ago. So the Lunar Orbiter spacecraft were in orbit, the first orbiters of the moon. When scientists on the Earth were tracking that orbit, what they found was the lunar orbiter was never quite exactly where they expected it to be. The orbit of the satellite was being perturbed by something, and that something was subtle variations in the gravity field of the moon. So back as early as 1967, we were able to detect variability in the moon's gravity field because of its interior structure. Fast forward, this is a gravity map of the moon, circa late 90s, early 2000s. This is from the Lunar Prospector Orbiter, where now, with more sensitive measurements tracking an orbiter around the moon, we can create a full global gravity map where reds are positive high gravity anomalies from excess mass and blues are negative anomalies. And this is an incredible tool for probing the structure of the moon. However, if you look at this is centered on the far side of the moon. Here's the near side. Notice in the far side, it gets all stripy and kind of ugly looking. It's looking pretty good on the near side, pretty bad on the far side. This is because this data is taken from tracking the orbit of a spacecraft. Well, what happens when the spacecraft goes over the far side? You can't see it anymore, and you can't track it anymore. So up until very recently, our gravity data from the far side of the moon was really quite poor. And that's where a recent NASA mission called GRAIL, the Gravity Recovery and Interior Laboratory, comes in. And this is a mission that I was fortunate enough to play a small role in. But this was a designated mission to study the gravity field of the moon. What was unique about this mission is two things. One is that it consists of not one, but two satellites, two spacecraft orbiting the moon in tandem, basically just measuring the distance between those two satellites. The reason why you do that is because with these two satellites orbiting, one a little bit in front and one a little bit behind, that front spacecraft encounters a little gravity anomaly before the back one does, and it speeds up or it slows down, and that back spacecraft either catches up a little bit or falls further behind. So if you're always measuring the distance between these two satellites, you're really measuring variations in the gravity field, and they can keep tracking one another even when they're on the far side of the moon. So that's one of the really important things about GRAIL. And the other thing is its orbit altitude. It orbited incredibly low to the surface of the moon. This is a map of the minimum altitude of the spacecraft as a function of location on the lunar surface. The orbit was changing now and then, so you see a lot of variability. But what you'll notice is that a lot of the moon is covered in these deep shades of blue, orbits less than about 8 kilometers. Now, if anybody pays attention to satellite orbits, that is incredibly low. that is much lower than any satellite has ever orbited another body before. For comparison, the Mars Reconnaissance Orbiter, an orbiter of Mars from which we have gravity data from Mars, orbited at about 300 kilometers above the surface. Goche, which was a real cutting-edge gravity mission to the Earth, orbited at an altitude of about 220 kilometers. 747 cruising altitude, somewhere around 13 kilometers, about 40,000 feet. GRAIL, getting much of the moon's surface about 8 kilometers, that's lower than a typical airliner is flying. So picture next time you're flying in an airplane, just look out the window and imagine looking down below you and seeing two spacecraft going zipping by at a speed fast enough that you probably wouldn't see them zip by. And that's what GRAIL was doing. We can't do this on the Earth because the Earth has this pesky, annoying atmosphere that just ruins all of our gravity observations. On the moon, without an atmosphere, we can orbit as low as we want, and eventually those two satellites orbited at 0 kilometer altitude, and they just smacked into the lunar surface, and that was the end of the mission. It was planned, not an accident. But because of that low orbit altitude, we've got better gravity data for the moon than we have for any other body in the solar system, including Earth. We have a better global gravity model for the moon than Earth. And that to me is pretty impressive. This is a map of the gravity field of the moon. But before I talk about this and talk about what we learn about the moon from this, I want to give you just kind of like a 5-slide summary of the moon. So, introducing the moon, a few things everyone should know about the moon. One is that we think the moon formed in a giant impact about 4.5 billion years ago, when a giant protoplanet slammed into the Earth as the Earth was forming, launched material out into space. That material formed our moon. The moon began hot, at least the outer parts were molten early in its evolution, something we call a magma ocean. And this was the state of the moon until it started to solidify. And eventually this magma ocean solidified to make, similar to what we have on the Earth, a low density crust and a higher density mantle. And we need to know that to understand the gravity data we see. When we look at the surface of the moon, we see craters. We see craters everywhere. Craters of all sizes ranging from millimeters to thousands of kilometers. But craters are not all we see. There's a lot of other things on the moon. One of the things we see, glance up at the full moon, the man on the moon, those dark spots are volcanic plains, lava flows called maria. And so this is something you can just see with your naked eye. So there's been volcanic activity on the moon. For me, as a geophysicist, as a geodynamicist, I really want to understand the dynamic activity of the moon. And for that, I'm interested in heat. Because the terrestrial planets, Mercury, Venus, Earth, Mars, the moon, internally driven activity is driven by heat. And that heat is produced by radioactive elements that are present in virtually all rocks. So the big ones for the interior of the terrestrial planets are uranium, thorium, and potassium. Trace amounts of these radioactive elements give off heat. It's not a lot of heat, but add that up over the entire interior of a planet, and it's enough to drive things like volcanoes, earthquakes, plate tectonics, the Catalina Mountains. All of these are ultimately driven by heat produced in the Earth, and the moon would have had radioactive heat as well. But it's the nature of radioactivity that it decreases over time. So in the earliest history of the moon, 4.5 billion years ago, you had a lot more heat being generated in its interior than we have today. And so if we're interested in dynamic, internally driven activity, it's that first 500 billion years is really where all the action should be. But we also know that there's craters on the moon. And we know craters are still forming today. We see them forming today. But the rate of cratering was much, much higher as you go back in time. In particular, about 4 billion years ago, the crater flux was orders of magnitude greater than it is today. And because of this, the oldest surfaces of the moon are in something called crater saturation. Basically, every square inch is covered by craters. You have craters on top of craters. Every new crater that forms is destroying an old crater. The frustrating thing about this is that this is the period of time when the moon had the most internally driven activity, volcanism, tectonism, all that cool stuff that I want to know about, but I look at the surface and all I see are the craters, which of course are interesting in their own right, but I want to know what else was happening on the moon, and that's where gravity data is key. We can take gravity and look through those craters to see what's going on within the crust, within the mantle below, and say something about early lunar evolution. All right, so now getting to this GRAIL gravity data. There's a couple of basic terms and basic concepts that I want to get across first before we really try to interpret this data. This is a map of the GRAIL gravity data. It's something that we call free air gravity. That's just the gravity as you would measure it. If you're standing on the surface, if you've got a satellite, this is the gravity field as you measure it. But when you look at this, what you see is a lot of craters. The stuff that I was saying I want to be able to see through to the interior. But here, these craters, this is all driven by topography. Just like Everest and Pratt knew that the topography of the Himalayas should produce a gravitational attraction that they could calculate, we know that the topography of the moon should produce a gravitational attraction that we can similarly calculate. And so we can do this just like Everest and Pratt. We can calculate the gravity field of the moon as we would expect it to be from topography. We can subtract that from what we actually observe and see where the differences lie. That gives us something called Bouguer gravity. Just think of this as these are the gravity anomalies arising from the interior, arising from beneath the surface. Now all those little craters go away and we can see deeper structures. And this is what we want to interpret. There's one more thing that I'm going to show you that I'll present a lot in this talk, and that's something called gravity gradients, which is this bottom plot here. This is basically just the slope of the gravity field. It's highlighting areas where the gravity field is changing, as opposed to areas where it's all the same within a broad region. Think of this as just like an image processing technique to bring out the transitions. Put your photos in Photoshop and stretch the contrast to see the details better. That's kind of what we're doing with these gravity gradients here. All right, so looking at this gravity gradient map, looking at this in the GRAIL data, we see a lot of things that we knew about. All of these circular bullseyes, those are impact basins. And I'm going to talk about those a little bit later. But when I looked at this data the first time, what I was most excited by was the things that I didn't know were there at all. So here I'm highlighting in the lighter tones all these lines crisscrossing the moon. These were a complete surprise, something we didn't know about, but were just jumping out very prominently in the gravity data. Here's a blow up of one of these on the far side, this striking line arcing across the lunar surface. When we look in topography data, there's nothing there. When we look in image data, there's nothing there. This is something contained entirely within the interior of the moon that we didn't know about before GRAIL. Here's another one of these on the far side. Again, about 300 kilometers long, it's about 200 miles. Long linear anomaly, again in topography, in image data, and every other data set we look at, nothing. This is a subsurface anomaly that we discovered with GRAIL. So what are all these lines? Why are all these lines crisscrossing the moon? Well, when we looked at the actual gravity anomalies, we see a big positive gravity anomaly going across these lines. That tells us there's excess mass. There's a mass excess in the subsurface. From geology, the one thing we know of that can do that would be a long plane of dense rock, something like a dense igneous rock. That's what we would describe as a dike, where magma intrudes into the crust along a plane and then solidifies, and that solidified magma is more dense than the typical rocks around it. So that shows up strongly in the gravity data. So here, not too far away, we've got Shiprock in New Mexico. We drive past this on our way to Colorado. Really dramatic features if you haven't seen them. But what Shiprock is an ancient eroded volcano, where this is the core of the volcano, and this long linear ridge is a dike. That dike formed deep beneath the surface, but because of erosion, we can see it sticking up today as a ridge. This is similar to what we think these long lines in the gravity data on the moon are, although those gravity anomalies we see on the moon are about 1,000 times larger than this. So next time, if you're out driving or visiting Shiprock, look at that and picture it 1,000 times larger. And that's what was forming on the early moon. So now we know that there's this very ancient population of enormous dikes, of solidified magma bodies in the lunar crust, older than the surface we see, older than the craters we see all over the surface. So dating from the earliest evolution of the moon. Why on Earth is that the case? Or why on the moon is that the case? Well, one thing that tells us is that the moon was expanding. You had to make room for all that magma. If the moon was expanding, its outermost shell, its outer crust, would crack and fracture, and that would make room for the magma to intrude. So now we think that the earliest moon was expanding, and expanding by kilometers, by miles. This is not a small amount. How could that happen? Well, so far, two theories have been proposed. One idea, if you go back to earliest lunar evolution, where you've got a hot magma ocean over a cool interior, that's not stable. As this interior warms up, it'll expand, as solids do when they warm up. and that could cause the cracking and the dikes that we see. It's also thought that as the moon's magma ocean evolved, in those last liquids as it was crystallizing, you put all of those radioactive heat-producing elements in there, and then they sunk deep into the interior. Put all those radioactive elements into the deep interior of the moon, and it warms up the entire moon, and the moon expands. These are two completely different scenarios that would have the same effect, that can both explain what we observe. We don't know which one of these are correct, but they're telling us something about early lunar evolution that we're still trying to understand here. All right, now I want to change gears and talk about impact basins. This is something you can see with your eye. Look up at the moon, and those dark spots, as I said, they're volcanic plains, but if you look closely, a lot of them are pretty round, pretty darn circular. And that's not a coincidence. These volcanic plains formed inside of ancient impact basins. This was actually noted in an early seminal paper, really pivotal paper published right here at the Lunar and Planetary Lab. So a young grad student named Bill Hartman and his advisor, Gerard Kuiper, who this building is named after, published a paper in 1962 about concentric structures around lunar impact basins. This was really a defining paper that first described these rings around basins, around giant impact basins on the moon, and also made a very important discovery of a new impact basin that was unknown at the time. See, on the edge of the moon, as we see it from Earth, there's an impact basin sitting right on the edge, but we're looking at it edge on, which is not a good angle to see things from the Earth. Now, we didn't have any orbiters to take pictures of this at this time, but Hartman and Kuiper did a really ingenious low-tech thing here. They took a picture of the moon and they projected it on a sphere. Then all they had to do is just walk around to the side of that sphere, and they could get the side view of the moon that otherwise you'd only get from an orbiter. I think this is brilliant. Nowadays we could write computer codes to do the same thing, but a slide projector and a basketball, or probably wasn't a basketball, but a sphere does the same thing. When they did that and walked around to the side of their projected moon, they saw all of these arcuate structures surrounding a point just out of view. And they said, that looks a lot like what we see in these things we're interpreting in impact basins on the near side. They named this the Oriental Basin. We now know that Oriental is the youngest, freshest, best preserved impact basin. If you want to understand impact basins, Oriental is your go-to basin. And that was discovered right here. When they looked at this, they said, all of these scarps, that looks kind of like a fault scarp, a cliff that has a fault underneath it extending down into the Earth. So they interpreted there to be faults underlying these scarps, penetrating deep into the lunar interior. When they looked, they saw dark patches in some of those rings, and they said that looks like lava. That looks like volcanic deposits. We think that maybe that lava flowed up through those faults and erupted on the surface. At this time, in 1962, that was speculation based on some fuzzy Earth-based images. Now, 2017, we've got the data we can use to actually test their ideas. So this is the Oriental Basin as I typically think of it. This is a topography map of Oriental. You can see this central depression and these beautiful bullseye ring pattern around it. All of these red lines of mountains with scarps along the edges of it, that's what they were seeing in their images projected onto that sphere. Now we can take the topography, then look at the Bouguer gravity, looking into the subsurface of Oriental. What they were trying to interpret from their images, we can now image with gravity data. So here's the gravity map of Oriental. What I can then do is take that Bouguer gravity, this is topography on the left, and I'm taking that gravity to model what the crust-mantle interface would be. So if we've got a low-density crust on top of a high-density mantle, and that's the source of the gravity anomalies, we can use the gravity anomalies to figure out what that boundary between the crust and the mantle is doing. And here's a cross-section through that. What we see is that, well, within the center of the basin, the mantle's been lifted upwards, and the crust is thinner. Well, that's what we expect in a big impact. It should excavate out the crust. When we look outside the central region, in the surface, we see these wiggles that correspond to those scarps that you can see in the images. In the subsurface, we see the same wiggles, and they're parallel to what's going on at the surface, but shifted over by a little bit. This is telling us that there are indeed faults originating at those rings, and that those faults go all the way through the lunar crust down into the lunar mantle. Now, while I've been using gravity data to try to understand the structure of the basin, a colleague of mine, Brandon Johnson at Brown, has been using models to investigate the impact process. So this is an animation of an impact as could produce the Oriental Basin. This is the asteroid right here. I'll point to this, that's about to strike the moon. And as we run this forward in time, you see this incredibly dynamic process where the crust and mantle are excavated, material splashes out into the outer regions. You see oscillations where the mantle is oscillating up and down by hundreds of kilometers, or at least in excess of 100 kilometers. An incredibly dynamic impact event with just amazing consequences. Here you can see that uplift of the mantle and that thinning of the crust that we're seeing from the GRAIL gravity data. But when Brandon looks at his models up close, you can see these sort of lines propagating through the models where all of his contour lines are deflected downward. Those are faults. His model's predicting faults to form and to cut all the way down to the crust-mantle interface, just like we see in the gravity data here, and just like Kuiper and Hartmann predicted, I guess 55 years ago. So another thing that they talked about was these dark volcanic deposits. We can now see these much more clearly, and indeed they do look very much like volcanic eruptions ponded within these rings. And then we can look in the gravity data, and here I'm showing the gravity gradients. And if I go back and forth, where we see that dark deposit, we also see gravity gradient anomalies. And in fact, they continue around and go all the way around the basin in this sort of bullseye pattern. When we analyze profiles of these gravity gradients, we see that they match what we'd expect for a ring dike, for dense igneous rock intruded into that fault. So again, what they were interpreting based on these images, we're now seeing very clearly in the gravity data and able to confirm. So Oriental is one of many basins, and we're looking at other impact basins. This is a set of basins on the moon: Oriental, Chrysium, Nectaris, Smithy. Some of these basins are showing similar things, and we've made really great strides in trying to understand the formation of these multi-ring basins based on this gravity data. Some of these basins are actually showing different things, so we don't yet have the whole story. Some basins show structures very unlike what we see at Oriental, so there's still a lot of work left to be done to understand this process of giant impacts on the moon. Now, speaking of giant impacts, there's one region on the moon where the largest impact has been proposed to occur, and this is in fact the area on the moon that you're most familiar with. So when you look up at the moon, see the man on the moon, rabbit on the moon is what the Chinese say, which I think is a lot more accurate. I can't see a man, but I can see a rabbit. But all these dark spots make an area that is somewhat roundish in pattern. So early workers noted this and said, well, you know, this looks a lot like it could be a giant impact basin. Just like we see lava ponded within these smaller basins like Imbrium and Serenitatis and Chrysium, well, maybe this big concentration of lava here is ponded within one single giant basin. So this was named the Procellarum Basin, an enormous basin encompassing much of the near side, but a very controversial basin, because unlike these younger basins, a lot of the telltale signs of an impact crater really weren't there. So this has been a matter of debate in the field for some time. As you can imagine, if we could look into the subsurface to see the subsurface structure of Procellarum, maybe we could say something more about this. So here I'm showing a topography map of the moon. And this is a funny projection, but centered on that Procellarum basin. And you see, well, the near side of the moon has all this low topography in this area. You can imagine how you could trace a circle in this area and make that the rim of the basin and make this look like other basins like Imbrium, like Oriental. And so to first order, the idea of a Procellarum impact basin seems reasonable. But now let's look in the gravity data. Let's look beneath the surface and see what we see. This is a gravity gradient map of the same region, and we do see structures. Something very dramatic is happening in this region, but it looks kind of square. We see a lot of straight sides. We see sharp angles, right angle corners here. There is a giant square on the near side of the moon, almost 2,000 kilometers across, and we didn't know about it before we had GRAIL data in hand. That to me is pretty impressive, but from the standpoint of an impact, well, that nice circular basin that we were looking for, what we see is a square. And the problem is that impact craters, generally speaking, aren't square. They generally don't have straight sides. They typically don't have corners. As an example, you could argue, oh, but when things get big, all bets are off, right? But this is a giant impact basin on Mars called the Borealis Basin. This is topography and kind of a modeled crustal thickness. And it's round. It's elliptical, just like most basins are. So most basins are actually more elliptical than circular, but they've got a pretty consistent size and shape. Procellarum is quite a bit smaller than that, and it's a giant rectangular square. So this really doesn't match what we expected to see in looking for an impact basin, and so we want to look for other hypotheses to try to explain it. Now this is still a big puzzle. What we can do with gravity data, we can try to model the subsurface structure. This area, as I said, has been flooded with a lot of lava. Igneous rocks tend to be more dense. And so if we want to look at the structure, we want to look at both the thickness of that low density crust as well as the thickness of the lava. And we have to take both of those into account. But here in this Procellarum region, again, we've got this crazy square type pattern. If we look at a few of these border structures in detail and look at cross-section through those, so this is the gravity data. This is a cross-section through the structure as we model it based on the gravity data. And those long linear segments we see bordering this region, if we look at a cross-section through those, what we see is that the crust has gotten thinner. The mantle's been lifted up, and the lava, the mare there, has become thicker. This cross-section here, well, if we just look at the crustal part, that thin crust in a narrow zone, that's what you expect when the crust is rifting, when you've got extension, stretching and thinning out the crust, and then these volcanic eruptions then flooded the whole area in basalt and made these dark maria that we see today. And that's what we're interpreting this as. This is an image of the East African rift, one of the most famous rift valleys on the Earth. That is what we think is happening on the moon. Ancient, very ancient rifting was stretching apart the crust, causing these enormous tectonic patterns in this giant square pattern, and then the whole region got flooded with lava. Now this is a topographic map of the region around the East African Rift Valley called the Afar Triple Junction with the Red Sea, the Gulf of Aden, the East African Rift Valley here. As a geophysicist, as a theoretician, I have the privilege of being able to just take this whole area and flood the whole continent with lava. It's something that we can do in theory, but not in practice. So when I do that, I can then model the gravity field. This is what I would expect this area to look like if I were to flood it with lava in gravity data. And you see a structure, this sort of right angle pattern with this strong gravity gradient anomalies is very much what we're seeing in the GRAIL gravity data. So it seems to be a reasonable interpretation here. Now, just to try to give a visualization of what this might have looked like, I've tried to combine the GRAIL gravity data with images. They wouldn't have really looked like this, but it's a fun way to visualize it. So this is all data, but merging the GRAIL gravity with images of what these rift valleys would look like crossing the moon. I think this helps give you a sense of scale of these rifts just stretching off to the horizon. Here's another one here. Here's one where we see a pattern of two parallel rift valleys, something we also see very commonly in rift zones. And then superimposed on the moon as we see it from Earth, this giant square pattern of rift valleys. Now, we think this is what these structures actually are, but this is bizarre. I have to say, no one would have ever expected a rift valley on the moon. We don't have a better explanation of the gravity data, but rift valleys on the moon are just not something we talk about. We know about rift valleys on Earth. We know about rift valleys on Mars. We know about rift valleys on Venus. But the moon, this is something unexpected that we still really don't understand the processes responsible for and driving this. And that's kind of how the note I want to end on is really the dark secrets lurking behind the dark side of the moon. You know, the dark side of the moon symbolically in pop culture symbolizes the unknown. And one thing I want to convey to you, we've learned so much about the moon in the last 50 years worth of spacecraft exploration. It's incredible the data we have. It's incredible what we do know. But it's also amazing what we don't know about the Earth's nearest neighbor. And there's still a lot of work left to be done. And so I just want to talk a little bit about, in my mind, what some of these big questions, these big unanswered questions are regarding the moon. So one thing that we are still debating, we still don't understand, is how did the moon actually form? It's been agreed for quite some time now that the moon formed in a giant impact. And for a very long time, the whole community more or less agreed on what that impact looked like. You may have heard the story of a Mars-sized object slammed into the Earth, blasted ejecta out, and that ejecta coalesced to form the Earth's moon. That explains many of the observations of the moon, but there's a few key ones that it doesn't even come close to explaining. In particular, the Earth and Moon are almost identical in composition, and that's not what this model predicts. And so just in the last several years, new theories have come out, also revolving around giant impacts, but very, very different impacts. In one view, there are two almost identically sized objects strike one another, and in that, the result of that impact, the material blasted out again forms the moon. But this is a completely different type of impact than was envisioned before, with very different consequences. In another very different scenario, the early Earth was rotating incredibly fast. It was spinning very quickly, almost as fast as it's possible for it to spin before it becomes unstable and breaks apart. And at that point in time, an object strikes the Earth, and that smaller, faster impact blasts material into orbit, which forms the moon. These are very different scenarios with very different predictions in a lot of respects, but they can both give us a moon-like object in orbit around the Earth. We don't know the answer, and both of these theories have problems. Now, the formation of the moon is not just the formation of the moon, it's also the biggest thing that happened to the Earth. We don't understand the Earth until we understand where the moon came from, and that's still an area of intense debate in the field. For me personally, the one thing I struggle with most in lunar science is the fact that the moon is lopsided in just a fundamental way. So this is a visible image map of the moon centered on the far side. What you see, the near side has all those dark patches, that basaltic maria. The far side has very few. This was actually first discovered in a Soviet mission, the first mission to fly past the moon, where the Soviet mission then turned its cameras back to the moon and took a picture and surprised everyone with the fact that the far side of the moon looked nothing like the near side of the moon. But it's not just in pictures that the near side and far side look so different. This is a topographic map of the moon. The far side is all high elevation. The near side is all low elevation. It is just fundamentally lopsided. The same thing extends to the thickness of the crust. The far side of the moon has a very thick crust. The near side has a very thin crust. This also extends to composition. This is a map of the distribution of thorium. Thorium is one of those radioactive elements that's responsible for driving internal activity, for heat production and geodynamic activity on the moon. In this map of the thorium, what you see is all the thorium is concentrated on the near side. Very little of it is on the far side. So composition, topography, just visible appearance, the far side and near side are fundamentally different, and we fundamentally do not know why. There really aren't even many good theories to explain this. My postdoc Alex and I argue about this all the time. We just had a 3-hour heated debate about different theories to try to explain this. And I can't say we've got any very good ideas. We have ideas, but not necessarily good ones. This is something that we don't understand, and this is the most basic aspect of the moon. In this sense, I think lunar science is very similar to Earth science back in the days before we understood plate tectonics. So plate tectonics is how our continents drift around, how ocean basins form. Plate tectonics is fundamentally what drives and explains the Earth. Well, this near side, far side asymmetry is in many respects the most fundamental aspect of the moon, and we still can't explain it. And then just this overall question of what drives early lunar dynamics? Why do we see all these dikes formed? Why was the early moon expanding? Why was there rifting around the Procellarum region? Another big question, why was there a magnetic field on the moon? This is something I didn't talk about, but something my postdoc Alex is working on. The early moon had a magnetic field very much like the Earth's. And the troubling thing is that magnetic field was too strong. It was active for too long. And we can't come up with a mechanism to explain that. And that is a big question that still needs to be answered. And so I just want to wrap up then by saying the moon is an incredible place. We have incredible data from the moon. Not only gravity data, topography, images, all sorts of remote sensing data sets. We're learning all sorts of things about the moon, about the lunar surface, as well as about the lunar interior. And yet still, more than 50 years after people walked on the moon, we're still grappling to understand some of these fundamental questions. And so that's, in my mind, why lunar science is still an exciting field. With that, I'll just wrap up, and I think we've got time for a few questions.
There's a
I guess we
microphone
got a
coming. Just a
microphone
second.
there next to you.
Which theory do you believe most closely in of how the moon formed?
Either or neither. They both have some challenges to them, to be honest. You know, these two objects of exactly the same size hitting each other, well, that may not be the most probable thing that you would expect to see. At the same time, to get the Earth spinning as fast as it had to be spinning for the other hypothesis to work, that's also difficult to do. One of them may be right. Improbable is not impossible, and improbable things happen all the time. Surf the internet, and there's enough people in the world that something incredibly improbable has happened to everyone out there. So maybe one of these improbable events is the answer for the moon, but I can't say I've got a favorite.
Thank you.
Other questions?
Is it possible that the lopsided part of the moon could have something to do similar to like how moons like Titan are warped by the high amount of gravity? So that's why they're so volcanically active?
So yeah, so tidal effects is a very attractive explanation for it. Because, you know, if the side facing the Earth is so different than the side facing away from the Earth itself, you want to play a role in that. Tides are one thing to do that. Tidal heating is one. The one problem with tides is that if you go to the beach and sit for a day, I highly recommend you spend a day at the beach. What you'll notice, high tide happens twice a day because the tides are actually symmetric. So the Earth has raises a tidal bulge on the near side of the moon as well as on the far side of the moon. And actually, that's a very good question because we see that pattern. We actually see these two opposing bulges on the moon that are explained as a result of tidal processes very early in the moon's evolution. It's also true that the tides are ever so slightly asymmetric. The Earth side bulge is a little bit larger. And that's something I've explored. Could we do this if the moon was really close to the Earth? In theory, yes. In practice, I think probably no. So very good question, though.
You've talked about GRAIL and its importance to you. I'm just curious, where do you place the manned missions that we put on the moon, including a geologist, in terms of the information gained from physically going there versus the other ways that we've looked at the moon?
Critically important. So the whole idea of the magma ocean and the earliest evolution of the moon based on that comes out of the samples the Apollo astronauts brought back. In terms of, they brought back all of these rocks rich in a mineral called plagioclase, which is sort of a dead ringer for a magma ocean. Another thing, that concentration of thorium I showed on the near side, that is this big question that we're trying to understand, that was first discovered from the rocks brought back by the Apollo astronauts, where some of them were rich in creep, we call it. So they were creep rich or creepy. And that was something discovered by the Apollo astronauts. Seismic data from the seismometers they put on the surface. I think that combination of boots on the ground, landers on the ground, as well as orbiters is really, really what has been critical in understanding the moon and hopefully other planets.
Yeah, I have a question about the gravity on the moon. Is that determined by the size of the moon, the fact that it has no atmosphere, its proximity to us?
So the average gravity is basically the size of the moon, like you said. So mass and radius both come into gravity. And then in the end, you can roughly estimate gravity based on the radius. So it scales almost linearly with radius. So if the moon is a fifth the size of the Earth, it should have about the fifth the gravity. It's not quite like that, but very much size dependent.
What was your work on the GRAIL project? Like, what did you do?
So I was a late addition to the GRAIL team, which meant I did none of the hard work to develop the mission and make it fly, and got to have all of the fun with playing the data.
So I was wondering, how similar is the GRAIL mission to the Dawn mission?
So we get gravity from both. With GRAIL, the key things about GRAIL, being lower to the surface, and also that having two spacecraft really helps you get the precision you need. But Dawn has given us some really impressive gravity data, lower in resolution, and yet at the same time, that's the first gravity data we've got from Vesta and so on.
So a question about related to the lopsidedness you talked about. Seems like the photos you showed show mostly craters, lots more craters on the far side, which you said is higher elevation. So is that explained sort of simplistically because of the fact the near side is lower and that the craters were filled in then by later lava flows?
That's most of it. And actually, one of the things we can do with GRAIL that Alex, who I work with, has been doing is actually you can take a crater and fill it in with lava so you can't see it anymore. It's harder to hide it from gravity. And so he's using the GRAIL to actually see those craters buried beneath those volcanic plains. Many are there, not quite as many as you'd expect, and that's interesting.
So you're saying that the lunar magnetic field was too strong? So you're saying that the lunar magnetic field was too strong for too long? Could that have something to do with like specific densities of the material or like the composition of the moon?
I wish I knew. We really don't have an answer. What Alex has been doing is just going through every possible energy source to drive it. Combination of adding different elements to the core to increase that density contrast, adding more heat, doing whatever he can, really going beyond the bounds of plausibility and still not able to reproduce it. So we're still looking for an answer on that one.
Other questions? Okay, one here and then one there.
The effect of the moon on the development of life on Earth?
Yeah, so the moon, and like I said, the moon forming impact is the biggest thing that happened to the Earth, and we absolutely would not be here without the moon. One good point of comparison is Mars. The Earth has a really big moon which really stabilizes our spin axis. So the spin axis of the Earth, it wiggles a little bit. Mars, without a big moon, its spin axis goes up and down the full 90 degrees. You can have the poles of Mars pointing straight at the sun. You can have the equator of Mars pointing straight at the sun. Because that Mars has enormous, enormous climate changes, the kind of thing that we'd be pretty hard-pressed to deal with here on Earth. So I'd say the moon has an important influence on life on Earth today. And then, of course, who knows what our planet would look like without that impact? That's anybody's guess.
So since the astronauts generally landed on like around the same area, since the moon is so lopsided, if we landed on the far side, could we have possibly gotten like different samples that told us something else?
Absolutely. And one thing that we do have going for us, all of our samples are from a fairly small patch on the near side of the moon, except for lunar meteorites. It turns out there's meteorites that you can pick up on the surface of the Earth that actually got launched off of the surface of the moon. We don't know where those came from, but we think they'd be more or less randomly distributed. So that's the one way we can sample the far side of the moon, is by looking at these meteorites and saying, well, statistically, half of them should come from the far side. The problem is, unlike the Apollo samples where we know exactly where those were picked up, each meteorite could be from anywhere. And so there's a lot of interest in getting samples from the far side.
Okay, one last question. All right, then let's thank Dr. Andrews-Hanna.
Thank you.